The last topic we're going to talk about is graphing polynomials in general. And so before we begin, let's take a look at a polynomial. We're going to call him P of X. And it's going to be x squared. How about minus 100x? And we'll go plus 1. Now, something to notice here is this is a very big number, this 100 out in front of that x. And at first, when we start, we're going to plug in a bunch of numbers here. And when we first do that, if we start with a small number, let's just say 2. Let's say we plug in the number 2 and see what we get. We get, okay, 2 squared minus 100 times 2 plus 1. Let's see what's happening here. 2 squared is just 4. But minus 100 times 2 is minus 200 plus 1. Right now, when the input is small, then this term right here, and by term, I mean the variable and its coefficient right here, the x to the first term, dominates. This term right here dominates the expression, right? It's much, much, much bigger in magnitude than everything else. And as a matter of fact, if we wanted to approximate this, we'd say, well, this is almost, it's about equal to 200. And you are minus 200, sorry, and you wouldn't be too far off, right? When you actually do it, actually evaluate it, you have 4 plus 1 is 5, so 5 minus 200 is negative 195. And you can see, like, yeah, we're not that far off. It's like this term is pretty much taking over the whole polynomial right here. But watch what happens when we plug in bigger and bigger numbers. Okay, so at first, what I'm going to do, let's try 10. 10 is not that big, not very big at all. We have 10 squared minus 100 times 10 plus 1. And let's see, 10 squared, 10 times 10, that would be 100. Okay, minus 100 times 10, well, we're throwing on one more 0, so that's 1,000 plus 1. And we could see, okay, this term is still dominating the equation, right? It's still the bread and butter of what's going on. In fact, it's about 10 times bigger than this term right here, right? The middle term is about 10 times bigger than, it's exactly 10 times bigger than the x squared term. And so it's still the case right now that the x term, this term right here, is still dominating the entire polynomial. And this is indeed how we say it. We say dominating, that this term dominates the polynomial here. But watch what happens when we throw in a much bigger number. Let's just go for broke and plug in 1,000 and see what we get. We get 1,000 squared minus 100 times 1,000 plus 1. Okay, 100 times 1,000. That just throws on 2 more zeros. So 1, 2, 3, that's minus 100,000. Now we can see what's about to happen, right? 1,000 times 1,000, that will be a 1 with 6 zeros after it, or 1,000,000. 1, 2, 3, 1, 2, 3. And now what's happening is that this term is bigger. This term here, the squared term, is starting to dominate. This term is starting to dominate the entire expression, right? And if we were to add all of this up, we'd have 1,000,001 minus 100,000. And so I guess we'd have, what would that be? I don't know. I don't care. It doesn't matter. it's like 900 something, like 900,000 or something like that, right? And I guess 900,001. I probably did that wrong. Whatever. I got COVID. I ain't worried about it. The point, though, is that the bigger number that you plug in, right, even though this coefficient out in front of the x term, even though it's very, very big, eventually, as we plug in bigger and bigger numbers, it doesn't matter how big that 100 term gets. Eventually, if you plug in a big enough number, this squared term is going to end up being much bigger than anything here, right? And for instance, just to really drive the point home, we are going to plug in 1,000,000 into here. We're going to evaluate P of 1,000,000. So that is 1 with 6 zeros after it. We take that and plug it in. We have 1,000,000 squared minus 100 times 1,000,000 plus 1. 1,000,000 squared is 1,000,000 times 1,000,000. So that should be a 1 with 1, 2, 3, 6. It should be 1 with 12 zeros behind it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minus, it's 1,000,000. Add on another 2 zeros. That's 100 million. 100 million plus 1. And now take a look at what's happening, right? Like you're going to take, I guess this is a million, that would be millions, that would be billions. That's 1 trillion. You take 1 trillion minus 100 million. It's really, and as you could see, if we were to do that, line that up right underneath it, you could see what's happening, right? That this is becoming less and less a proportion of the whole thing. Like when we first started, this was 200 and this was only 4. This one was way, way, way bigger. Plugged in 1,000, they were off by, like 100,000, or they were off by like 1 order of magnitude. But now, look at that. This is 1,000 times bigger than the middle term. Okay, so I didn't bother to plug in negative numbers. We could have done the same thing with negative numbers. I could have started with a -2 here, negative 1,000 here, negative 1,000,000, and the conclusion is going to be the same. And that's that as the input gets bigger and bigger in either direction, either in the positive direction or the negative direction, when the input gets bigger, then the highest order term of the polynomial dominates the entire polynomial. Any questions with that? Are you following what I'm saying here?
I think I'm following.
All we're saying is that you take something and raise it to a power, right? Eventually, yeah, it might not beat out the other one at first, but eventually, if you plug in a big enough number, then the thing to the higher power, so something squared, is going to be much bigger than something to the first power, regardless of any coefficient you could put up in the front. You could say, well, Justin, what if it was 1,000,000 times x? Well, yeah, eventually plug in a couple billion, and that number, just like we saw before, will eventually become much, much, much bigger than that. And so much so that this thing is going to become more and more negligible, right? So like if you, for instance, if you had 1 trillion and you subtracted 3, you pretty much still have 1 trillion, right? Like if you have $1 trillion and then you go and buy a cup of coffee, you still have $1 trillion, right? There's not much going on there. And that's what's going on with these polynomials, that when you plug in really, really, really big numbers, this stuff pretty much doesn't even come into play anymore. It becomes so small compared to the largest term that we could pretty much neglect it. And so that was a specific example of what we're going to be talking about here. And that is this. So let's write out a kind of general polynomial. I'm going to say some number a times x to some power n plus a bunch of other stuff. And then finally, we end up at, let's call it b x plus c. So you could imagine, like, for instance, if I had, don't bother writing this down, but what I'm saying here is we have something like, let's pretend 5x to the fourth plus 3x to the third minus 7x squared plus, how about 2x minus 5 right here? That's, we had something like that. We're saying, yes, the a is the 5 in this case. X to the n would be x to the fourth here. Then we have all those terms and blah, 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 blah. And then I'm just going to forget about it until the end where we have the 2 plays the role of the b and the negative 5 plays the role of the c right here. Okay, so the highest order term is this guy right here. It's what we mean by the highest order term, right? Order meaning like what power are you raising it to? I'm going to abbreviate that from now on as HOT, the highest order term. And we're going to say as x gets large, and I'm going to do that symbolically. We're saying as x goes in the positive direction towards infinity, or towards in the negative direction towards negative infinity, as x approaches plus and minus infinity, the highest order term dominates polynomial. That is, it takes over, right? Let's pretend here that I had, instead of 7x squared, let's say I had 700x squared. At first, when you're plugging in a 1 and a 2, this is going to be a really big term, and it's going to take over, right? It's going to be the biggest thing in there. Everything else will kind of be change, right? It'll be like a couple bucks here, a couple bucks there, but you're going to have a big number right there. But as we get bigger and bigger numbers, both in the positive direction and in the negative direction, this term right here is going to be way bigger than all of these other terms. And so as we go out to plus and minus infinity, this polynomial is going to look more and more like just this thing right here. And in fact, if I wanted to, I could say, well, if I wanted to draw something like this, and this is what this all comes down to, this is what we're talking about today. We're trying to draw polynomials. We'd say, well, I may not know the ins and outs of what happens. Like, I don't know exactly where this thing bends and curves and stuff like that, but I can tell you that when this thing gets really, really big, right, we don't really know what's going on close when x is close to 0. But as I get further and further out, I know that this polynomial is going to look more and more like this guy right here. And so, and it turns out that 5x to the fourth, if we just thought about 5x to the fourth, it would look something like this. Why is that? Well, you take any number, plug it in, you'd have a number to the fourth power, right? And so, okay, it's going to get bigger and bigger. They're also multiplying by 5, so it gets bigger and bigger. Also, since it's to the fourth power, you plug in a negative number, say like -1. -1 to the fourth is a positive number, times 5 is 5. Plug in a -2. -2 to the fourth is 2, 4, I guess, 16. Times 5 is whatever it is. It's still a big number and stuff like that. And so that is what 5x to the fourth looks like We don't know for this big thing, for this big polynomial here, we don't know what's going on here, but I can tell you that as, and here we go, as x approaches plus and minus infinity, the higher order term dominates, and so it's going to look something like this. You're going to see this a lot today. This is going to be kind of my notation for this type of thing. So if you just gave me this polynomial right here, this 5x to the fourth plus 3x cubed minus 700x squared plus 2x minus 5, I could tell you immediately just by looking at this. I could say, well, at some point, you may have to go really far. You might have to go out to 1,000,000 or whatever, but eventually, if you go far enough in these directions, this thing is going to look like regular old 5x to the fourth, which looks like this. And so it's going to be an upward facing cup like that. You following? Questions? Oh, you're muted, I think.
Yeah, I'm muted because I keep coughing and having to blow my nose.
I appreciate it. I appreciate that's nice. But are you following so far?
Yeah.
Okay, so just to really drive the point home, I want to graph this just to kind of prove what I'm talking about here. Give me just a second to pull this up. Actually, and if you could, would you go ahead and cut off your video so I don't have to like put a little thing over your video? I'd appreciate that. Okay, so let me share my stuff. Brave browser, there we go. Okay, so let's take a look at first 5x to the fourth. Oh, just like I said, it's a cup. Yep, go figure. Now let's take a look at 5x to the fourth plus 3x cubed minus 700x squared plus 2x, plus 2x, finally minus 5, this random polynomial that I did. And right here, you're looking at this and you go, this looks nothing like what you drew on the board. It's like, yeah, we haven't zoomed out far enough, because remember that 700 right there, that minus 700x squared is going to make this, that's going to dominate for a long time. When you plug in a 1, right, you'll have 1 times 5, 1 times 3, 1 times 2, you'll add those together, you'll minus off a 5, that's chump change compared to the 700 that's there, right? So, but here we go, I really want, there it is. We didn't have to zoom out very long before that term, the 5x to the fourth, really takes over. And yeah, of course, it's not exactly the same as the red function, because we have a bunch of other terms there. But you could see that this thing looks like a cup as you get really far away from the origin. Does that make sense? What I'm saying here? Okay. Okay. So so that's the idea. Like, so again, we want to be able to graph polynomials, and we have this nifty fact that really, if we want to know what happens way out in this direction, all we got to do is look at the highest order term right there. Okay, now, hey, oh, thanks, buddy. Thank you. Now, what about really close to the origin? Oh, watch out, buddy, watch out. So, okay, so this. Now, when, no, you cannot play with that, sorry.
Hot.
This is hot, yeah.
Here.
No, come on.
Come sit with me, please. Peter.
So that's when you plug in really, really big numbers. What about when we're plugging in really, really small numbers? In other words, when we're really, really close to 0. just going to do this once to really drive the point home. Let's say we're really close to 0. Here, let's think of a number that's really close to 0. How about 1/1000? That is very close to 0. It's actually 0.001. We could write it that way if we wanted. But now let's see what happens if I plug that into this polynomial. I would have 5x to the 4th plus 3 times 1/1000 x to the 3rd. 700 1/1000 squared plus 2 times 1/1000 minus 5. Okay, this thing right here, 1/1000 to the 4th power is 1/1000 times 1/1000, a total of 4 times, right? And that, I'm just going to add up zeros here. That's the same thing as a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros after it. That's a trillion. That's 1/1,000,000,000,000. That is a teeny tiny number. In fact, we could write it as 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's that number. And so we have 5 times that, or point bunch of zeros, 5. That's what that works out to. A trillionth, or 5 trillionths, plus, we did that with 1,000, same kind of reasoning here. 1/1000 times 1/1000 times 1/1000 would be 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, then times 3. So 1, 2, 3, 4, 5, 6, 7, 8, and then a 3. You can see what's happening, right? This is a tiny, tiny, tiny number. This is going to be a tiny, tiny, tiny number. This is also a tiny number, but not as tiny. But the thing that's really dominating here when we're very close to 0, is this guy. The -5 is not going to change. As a matter of fact, and then when we go and just plug in a 0, that's 0, that's 0, that's 0, that's 0. All that's left is -5. In fact, that's why we call this thing the Y-intercept. The last thing that's hanging out there is the Y-intercept because it's where it goes through the Y-axis. But the exact opposite thing happens, right? Like that happened before. It used to be that when x is a very big number, the highest order term dominates the entire equation, or the entire expression. But now when we're really, really, really close to 0, it's the lowest order terms that dominate. And I'm gonna in fact include the x term here in this. Let's see why in just a second. We call this the low order terms, the hots and the lots. And we have kind of the opposite relationship here. And it's that as x gets closer and closer to 0, or gets closer and closer to the origin, the low order terms dominate p of x. So let's take a look at the actual polynomial we have written up there. Could you kill your video for me, please?
Oops, wrong button.
Oops. Okay, so here we go. Graphing calculator. All right, so let's zoom in on this thing here. Of course, it goes through -5. We knew that it was going to go through -5 because when you plug in a 0, you get out at -5. And so it has to go through the y-axis at -5. But check this out. This is pretty cool. Notice that is not the tip of it. And if we zoom way in, this thing looks more and more. And look, I'm zooming in very far here. If you could see at the top, we have 1 times 10 to the negative 6. So that's a millionth. We're within a millionth of this thing. But as we zoom in really close here, this thing looks exactly like 2x minus 5. Drive that point home. Let's just graph 2x minus 5. 2x minus 5. Oh, it's right on top of it, isn't it? And that's because when these numbers are really, really, really small, when we're plugging in very small numbers, then when you take that and raise it to the 4th power, to the 3rd power, you're making it even smaller. And so very close to 0, your polynomial, the thing we're trying to graph, I'm zooming out now, and you can see it starts to break away from that line eventually. But when we're really close, those two, the line 2x minus 5 looks exactly like the polynomial we're trying to graph. So and then when we zoom way out, it looks like the highest order term, which is 5x to the 4th. Okay, so any questions thus far? I can't hear you if you said anything, so.
No.
No, okay. So now one important thing though is, so this just happened to be this way that I had 2x minus 5. What if I didn't have that x term? You might be willing to say, okay, well then if the low order terms dominate really close, then close to the origin, it should look something like this. And you would be wrong. You really don't want to look for a squared term. That it's for reasons we really can't get into. It only works, but the kind of analysis that we're talking about, the pictures that we are getting towards, only work with a single term. So like when we had 2x minus 5, then yes, then really close, it looked like the line 2x minus 5. But if you don't have that linear term, the x term, if your expression, your polynomial doesn't happen to have it, then it turns out that this thing is going to go through the y-axis in a straight horizontal line. Let me show you what I mean. Again, if you could kill your video, sorry. All right. So, okay. Still at minus 5. Come on. Okay, zooming in right here. All I'm going to do, I'm going to take the blue function and I'm just going to remove the plus 2x and see what happens. And you say, well, actually, Justin, that does look like minus 700x squared minus 5. And yeah, that's cool, but we can't generalize that. In this specific example, it happens to look like that. But what's always going to be true, always going to be true, is if you keep zooming in on it enough, if you get close enough, then the polynomial, the thing that we're trying to draw, the thing we care about, the blue function here, will look like a horizontal line right there. That's the big takeaway here. Like if it's not linear, right? If the last two terms, if there's not a pure x term, like when we had 2x minus 5, then it will always be a nice flat line right there by the origin. If it is a 2x or something like that, oops, plus 2x, something like that, then it will look like the line that it is. If it were a minus 2x, let's take a look at that. Oh, it looks like minus 2x minus 5 right there. If it were a minus 12x, it would look like the line minus 12x minus 5, and so on and so forth. Any questions? Is this making any sense? Anything confusing about this?
I don't think so.
Okay. So this is what we're gonna, so actually it's gonna kick us off in a few minutes. So let me show you how, when we come back, I will show you how we're going to use this information to try to get a picture of a given polynomial. I'm real bummed that we missed, that I didn't record that, but yeah. So, okay, the last thing is, what if they're not, all of the roots or terms are not to the power of 1? What if there's a different powers? What do we do? How do we deal with this? Well, the steps are going to be the same. We want to find the highest order term and the lowest order term. And it's really, we're going to do the exact same thing we did before. We don't have to multiply all these out. In fact, don't write down what I'm about to write down. But all this is, when you say to the fourth, that just means you have 4 of these guys, right? And so we could write it out like this. And then do this 3 times. And then say it's all of that stuff and then multiplied by -2. And we could go, okay, well then when I do my first, right, I'll have x squared and then blah, 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 bunch of inner, outer, last stuff. And then I'll have x squared that I'll distribute to give me an x cubed, blah, 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 blah. Or I could just say, well, hold up, how many x's do I have? That's what the highest order term is going to be. I'll have 1, 2, 3, 4, 5, 6, 7, 8 of them. X to the 8th will be my highest order term. We'll have a bunch of other stuff that we really don't care about. And then what about that last term? And again, if I didn't write it like this, we just go ahead and blindly just go through it and say, okay, well, -1 times -1 is +1, times -1 is -1, times -1 is +1, times -2 is -2, and then times negative, oh man, I shouldn't have done that. But anyway, another way we could do that is just to say, okay, well, what's -1 to the 4th power? -1 to the 4th times -2 times -3 to the 3rd. And that's essentially what I'm doing, right? I'm just kind of making it a bit more formal. We have -1 to the 4th is just +1 times -2. -3 to the 3rd is -27. -2 and 27, that's a 4 and a 1 and a 4 and a 54. A +54 should be done. So remember, so what did I just do? Well, I just said, if I were multiplying this thing out, I would go first, outer, inner, last, and I'd have, in the end, I would have a +1 over there as my last. And then I'd distribute those guys through, and my -1 would come in and all this and blah, 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 blah. And so ultimately, to get the last term, I'm just multiplying all of these constants by each other to get finally +54, like that. That makes sense, how I got that?
Yeah, I think so.
It's the same thing as if like when I first did this, when it was just 1, 2, and 3, I did first, outer, inner, last with the first, and I had a +2 as my far right thing. And then when I distributed the -3 in, the -3 hit the +2 to give me a -6. Well, now I'm just imagining I'm doing that, 8 times with all of these terms. And I'm just saying, well, then the far left thing is going to be whatever I get when I do that one and that one, which gives me a +1, which then I'll take that and multiply it by that one, which then I'll take and multiply by, and the last term is what I get whenever I just multiply all of these out. And so we have a highest order term. We have a lowest order term. Although I have not distributed these guys back in, and so let's get that. We're going to say the -2 is going to come back in to give me a -2x to the 8 is my highest order term. The -2 comes back in to give me a -108 is my lowest order term. And now I'm going to use those to get my overall picture of what's going on. So can I get rid of these two things right here?
Yes.
So thumbnail sketch of what's going on. Okay, I have an even power. And so it's going to either be an upward facing cup or a downward facing cup. It's -2, so it's got to be a downward facing cup. It has to go through the y-axis at -108. -108. Okay, now here's where it gets a little tricky, but it's not. If you just ask yourself these questions in the order that I'm asking them, it takes all of the guesswork out of it. Okay, so let's work from left to right. Starting on the far left, I see it's got to come from down here. So he's got to come up. And oh, also, I'm sorry, my roots. I have a root at +1, +2, and +3. So there's 1, 2, and 3. Okay, so starting from the far left, he comes up from -infinity and hits -108. So there's -108. That looks terrible. And he's going to come up and touch 1. And the question is, does he bounce back down or does he go through? And this is this is a hard one. I mean, well, to actually get into this comes down to the fact that that is a even power. And oh, man, I know you just want to get this class over with, and it would take a long time to explain this. For right now, just use it as a rule of thumb that when it's even, the sign stays the same. If he's negative beforehand, he's going to be negative after. So he bounces, then comes up and hits 2. 2 is an odd power, so he has to go through. He'll go through there and come back and hit 3. Question is, does he go through or does he bounce back? And we can see that it's an odd power because 3 is odd. So it's going to have to go through this way. And then we could see long-term behavior. He's got to go down forever. And so there's that right there. And that's it. That's all there is to it. I really wish that we weren't so pressed for time, because I would love to explain why it bounces back instead of going through. But this is a great skill to have. This is a skill that you're gonna need a lot. Basically, it comes down to the fact that I can't let this go. We have to talk about this just real quick. So let's see what happens when you take a number over here. Take any number that's less than 1. I'm taking a number that is less than 1 and I plug it in here. I have some number that's less than 1 and I subtract off 1. Well, that's going to be a negative number, right? Like, let's take a number less than 1. How about 0.5? Okay, 0.5 is left. -1 is negative 0.5. That itself is a negative number. take a number that's less than 1 and subtract off 2, that is also a negative number, right? Like a number that's less than 1, how about -5 minus 2 is -7. It is also a negative number. Take a number that's less than 1 and subtract off 3, it's also a negative number. And so we're taking a negative number raised to the 4th, right? That's what that is. You have some negative number here, raise it to the 4th. You have some negative number here raised to the 3rd. And you have -2 times, well, a negative raised to the 4th is a positive number. A negative number raised to the 3rd is a negative number. And so you have -2 times a positive times a negative. Well, a positive times a negative is a negative. Negative times a negative is a positive, and you end up with a -2 times a positive number is itself a negative number. So, and this makes sense with what we're saying over here. You take a number that's less than 1, you plug it in here, you'll get a negative. Cubed is positive, that's negative, negative, blah, 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 blah. You should end up with a negative number, and that is indeed what we see. Whenever you plug in a number that is less than 1, you get a negative number. And that's what we're seeing right here. They're always negative. They're below the x-axis. Now, when you plug in a 1, obviously the entire thing goes to 0. It is a 0 of it. Plug in a 1, you get 1 minus 1, and you get a 0. So it doesn't matter what everything else is. It's just a big fat 0. So let's see what happens when we take a number x that's between 1 and 2 and see what happens. Okay. We'll have -2. Okay, great. Now, if you're between 1 and 2, right, then like let's say 1.5, plug that in, subtract off 1, you'll have a positive number. 1.5 minus 1 is 0.5, which is a positive number. You take that and raise it to the 4th power, okay? Now we took a number, say 1.5, and minus off 2, we should have a negative number because 2 is bigger. So 1.5 minus 2 is -0.5. It turns out to be a negative number. Again, take that same number right here. 1.5 minus off 3. Well, 3 is much bigger, so it's going to end up being a negative number. 3rd power. A positive to the 4th power is still positive. The middle one is still negative. The last one, a negative cubed, is still negative. Negative times a negative is a positive. Positive times a positive is a positive. And then so then finally times -2 is still negative. We have when x is between 1 and 2, it's still negative no matter what. All of these numbers in here are negative because of this nifty little analysis we did right here. You take a positive to the 4th, it's still positive. These just always work out to be negative numbers. And so whenever you're between here and here, it has to be negative. One last bit, we're going to see why it has to be the case that when it's an odd root, it ends up going through. It's the last thing we're going to do right here. Let's say we take a number x. And let's pretend that x is between 2 and 3, and we plugged it in right here. We would have -2 times, and right now I'm just going to go ahead and do this. So a number bigger than 2 minus 1. So like 2.5 minus 1 is 1.5. It's still a positive number. So it's a positive number. Now take a number that's bigger than 2 and plug it into here, say 2.5. 2.5 minus 2 is 0.5. It's still a positive number. So that's a positive number. Okay. Now it's less than 3 though, right? So like 2.5 minus 3 would be minus 0.5. That would be a negative number. Okay, negative. And so negative 2 times a positive, that's a positive. Positive number times a positive number. Now, a negative number cubed is a negative number. So you have a positive times a positive is a positive, times a negative is just a negative. Negative 2 times a negative number is a positive number. And that is why all of those numbers, no matter where you are between 2 and 3, they're going to come out to be positive numbers. They have to be above. So that's where this weird little sign is. We call it sign analysis, S-I-G-N, because it's the sign of these numbers. Are they positive or are they negative? And it's that nifty little thing that happens that when it's to an even power, it doesn't matter whether that's positive or negative, it's always going to end up being positive. So when you cross over it, it doesn't matter. It's not going to change it. If it was negative to begin with, it's going to stay negative because that sign has not changed at all, right? It's always going to end up being positive. However, if the root, or I'm sorry, if the 0 that we have here is raised to an odd power, like this one is, then the sign does matter. And when you're on the left-hand side of it, it'll be negative. When you're on the right-hand side of it, it'll be positive. And so it will be different whether or how you look at it. Does that make some sense? It's very confusing stuff. Like I said, I really didn't even want to talk about it. But this just leads us to our rule of thumb that when the term, or when the 0 here is raised to an even power, it has to bounce back. And when it's raised to an odd power, it has to go through. Questions about that?
I don't think so.
Yeah, it's I remember when I was first introduced to this, and it was much more formal and well explained than the way I just did in the last 10 minutes trying to just throw this at you. I would suggest that you play with this a little bit. Like you could take this, if you don't believe this, I would suggest that you actually go through and take the numbers 0.5, 1.5, 2.5, and finally 3.5, and just plug them in individually and see what you get. When you plug in a 0.5, you'll notice, oh, you'll get a negative number here, positive, and so on and so forth, and just kind of follow it through and believe eventually that, yeah, it has to do this thing because this power is even. It has to go through because that power is odd. Although it's not like, it's the takeaway though is that all of this that we're doing with, is it positive, is it negative, and blah, 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 it's just so that we could know whether or not the graph of this thing goes through the root or does it bounce back. And the rule is that whenever the power of the thing is even, it will always bounce back. Whenever the power is odd, it will always go through, no matter what. And so if that's all you remember, if you can't justify it, that's okay. But this is a skill that you have to have. You have to be able to, given this thing right here, be able to draw this thing right here. And it comes down to, if it's even, bounces back. If it's odd, it passes through. So that's it. That's it for today. I'm sorry we are in our recording. We missed a good amount of what I said, and I hope that you have enough to go with for the homework. I'm gonna get it to you in just a second. Let me just I'm gonna look over the homework and make sure that, okay, so problem 1, it says for each function, determine the long-term behavior and the behavior near the origin by drawing a quick thumbnail sketch as we did in class. You do not need to include x-intercepts, but you do need to include the y-intercept. So what that is each one of those is some kind of polynomial. A polynomial like that. And what I'm looking for is that do I say to state it explicitly? No. All you got to do is draw the sketch. And you're going to say, okay, the highest order term is an even. And so it's a cup. And it is a positive number. So it's an upward facing cup. And so you do this. And then you say, okay, this one happens to have a linear term right there. So I would like to see minus 3x plus 2 would go through here at plus 2 and have a slope of minus 3. And so that's what I'm looking for question 1, something like that. For problem 2, it says draw a qualitatively accurate graph for each function. Be sure to label both the y-intercept and the x-intercepts. Explicitly state the highest and lowest order terms. So that's what we were just doing a second ago. So to be clear, if I gave you something like this, I would suggest that you start with the highest and lowest order term, of course, and that's what you're going to do. I'm going to say, okay, highest and lowest order terms. In order to do this, I'm going to say, okay, that's -7 times some polynomial. First outer inner last, that would give me an x squared would be the highest thing. And then we'd have that as x cubed. Okay, so x cubed has to be the biggest thing. Plus a bunch of stuff, we're not sure what. -1 squared is +1 times 2 is +2. So my lowest order term is going to be a 2 right there. -7 then is my highest order term. Two is my lowest order term. So that's what I mean by explicitly state the highest and lowest order terms. That's what I'm looking for that one. And then for the graphing part, we're going to say, okay, we have 2 zeros. This one's at x equals -2, and this one is at x equals 1. And so we have one here at x equals 1 and x equals -2. From this, I know that +2 is my lowest order term. So it has to go through up here at +2. From the highest and lowest order terms, I could do my nifty little analysis and say, okay, goes through here at 2. It's an odd power, so it goes like this, but it's flipped upside down. So it has to go up like that, down like that. And so I'm going to start from the left-hand side and say, okay, well, he's got to come from the top down. So he's going to come down like this. And then the question is, does it bounce back?
You're bouncing.
Uh-oh, that's not my lowest order term. Look what I did. Look what I did. So I'm sorry about this. I had negative 7x cubed plus a bunch of stuff. I don't know what it is, plus 2. But I didn't distribute that 7 in. I did it for the first one. I didn't do it here. The lowest order term should be a negative 14. Sorry about that. Sorry about that. Probably good that I messed up. That way we could see what it looks like when you mess up. Oh, let's not pull my computer around, buddy. Thank you. Please don't. Okay, so we got the correct highest order term, the correct lowest order term. Told me where that is. And I said, Peter, please stop. Decided to work from the left to the right, and so we had to come down from infinity in this way. Has to hit here. And then the question is, does he go through or does he bounce back? And so I look at that one and say, well, x plus 2 is where that came from. It's an odd power. Odd power must go through. So he goes through like that. Got to go through there at minus 14. And then, okay, he's got to make his way up to 1. So he's going to make his way back up to 1. And then the question is, does he go through or does he bounce back? Well, 1, that term is an even power. It's squared, so he has to bounce back down. So he bounces back down. And then I look back over here and say, oh, yep, he's going to have to continue down forever and forever. And so there's that right there. So that's what I'm looking for. This right here and this right here is what I'm looking for part 2.